and will tell us about commuting over Hamiltonian problems.
Okay. Thanks for the introduction. So, hi everyone. I'm Jiaqing from Caltech. I'm mainly working on local Hamiltonian problems, and today I'm going to give an introduction to commuting local Hamiltonian problem. So, this was based on 9 of previous work and my recent work with Sandy. So to begin with, I wish to draw your attention by asking a philosophy question. So I guess all of us love philosophy. So I guess probably half of the audience or most of the audience comes from a quantum information background. We live in a quantum world, and all of us more or less want to solve a quantum problem, like some problem in chemistry, physics, or some kind of entanglement problem. And all of those problems seems very challenging because of quantum mechanics. On the other hand, I guess probably some of you guys comes from a totally classical world. And we know in classical world, almost all problems are somehow equivalent to SAT. So SAT is a very old problem, and it has been studied for many years. And we already have quite a lot of algorithms for SAT. And some of them works very well in practice. So from this perspective, that we already have a lot of tools and algorithms for classical problems, and we want to solve quantum problems. From this perspective, need to be down, but very natural questions like, why don't we just use that solver to solve the quantum problem? So of course, we know it doesn't work because, I mean, everyone says quantum mechanics is more fancy. But what I really want to ask is like, instead of just saying no, do we know any better answer? It's like, in other words, I'm asking like, do we know what's the key property which makes quantum problem inherently different from classical? So this will be, the intuitive question for this talk. So different people definitely would have different answer. Some frequent answer would be because the quantum mechanics involves exponential Hilbert space, or some answer would be like because quantum mechanics has a sign problem. I think all of those are good answers. In this talk, we will try to intuitively answer this question from another perspective, which is inspired by uncertainty principle. So the details of uncertainty principle may not be very important, but the key information it gives is that like why quantum is different from classical. It's because in quantum world, we use non-commuting observables. So in summary, like today's focus will be like study the relationship between commutativity and the hardness of quantum problems. So in summary, today's key concept will be commuting. So let's be more specific. So today we will going to study a problem called commuting no Hamiltonian problem, and which is first introduced by Bravi and Viai in like 2023. In this talk, I will talk about motivations, and I will give overview of some results and the basic techniques. So, okay, let's go to the point. So I have said like the key concept in this talk will be commuting local Hamiltonian problems. So what is local Hamiltonian problem? If you are from a physics background, like you would know local Hamiltonian is a math tool to describe molecules and electrons. And if you are from computer science background, local Hamiltonian is just a quantum version of that. So to be more specific, in this problem, we are given a local Hamiltonian H, which is a quantum version of a constraint given to parameters A, B, and where H is supposed to be a local Hamiltonian, which is just an n-qubit Hermitian matrix, which can be written as the sum of local terms. And we typically will assume the parameters A, B to have a gap. And the key quantity we care about is the ground energy, which is the minimum eigenvalue of this matrix. And the local Hamiltonian problem itself is a decision version of ground energy estimation problem. So it's like given HAB, we want to decide whether the energy is low or high. So this is the definition. And one important fact you need to know for local Hamiltonian is like, so we say local Hamiltonian is a quantum version of 3-SAT. And we know 3-SAT is NP complete in classical world. So similarly, people can prove local Hamiltonian problem is QMA complete, where QMA is a quantum version of NP. So this is the local Hamiltonian problem. So as I said before, like today's focus would be commuting, and we will study commuting local Hamiltonian problem. So the only difference between general case and the commuting case is we, in addition, we assume all the local terms commute with each other. You may ask, okay, can you give an example of commuting Hamiltonian? Yes, like so for example, like 3 set is a special case of commuting Hamiltonian because it's diagonal in computed basis. And if you are from an error creating code background, commuting local Hamiltonian also contains all stabilizer codes. Famous example would be toric code or CSS code. If you are from physics, it also contains some interesting physics model like quantum double model. So this will be our key concept in this talk. So okay, before we go into any details, I wish to give you some intuitive thing. Like I wish to explain the intuitive thing about commuting local Hamiltonian. So as we said before, like the key concept in this talk would to study what's the complexity, like how hard is commuting local Hamiltonian. Is it hard as general case, or is in fact it's some kind of classical problem? So if you only want to remember one sentence for this talk, so I think the sentence should be commuting local Hamiltonian is simple but quantum. So what do I mean? So as in the introduction, like we inspired this problem from uncertainty principle. So from uncertainty principle, it seems like, I mean, we only involve commuting observables. It seems like this problem should be classical. So from this perspective, you might think, okay, probably commuting local Hamiltonian is classical. And from a technical reason, like commuting, just from linear algebra, all the terms commuting will imply you can diagonalize them in the same basis. So basically, I'm saying, like from a technical view, you might think, okay, after some basis changes, commuting local Hamiltonian will be similar to diagonal matrix, where the ground state will have a bit stream. So, but one thing you need to be careful is like, I mean, the unitary to diagonalize all those terms might be complex. But anyway, like from current slides, it seems very reasonable to conjecture commuting local Hamiltonian is in MP, is some kind of classical problems. Or more concretely, you might think, okay, what do I mean classical? So probably you might think, okay, commuting local Hamiltonian probably only involves classical system, which is of little entanglement. But unfortunately, this is not true. Like commuting local Hamiltonian is interesting not only because it's simple, but also it captures some very, very highly entangled quantum systems. So for example, as I said before, like people, okay, from first glance, you might conjecture commuting local Hamiltonian is some kind of classical system. And you conjecture probably you can always prepare the ground state by constant depth circuit, which is similar to that. But however, this is not true, like because we know there are counterexamples. So we know, for example, we know toric code is highly entangled, and people use such entanglement to do error corrections. And more concretely, we know like toric code has no constant depth ground state. So that's an example of commuting local Hamiltonian. Or more concretely, I mean, we care about the complexity. So more concretely, you may ask, okay, what's the upper bound of commuting local Hamiltonian problem? So currently, I think we don't really have upper bound. Like it still might be as hard as the general case, which is QMA1 complete. So the only difference we know between commuting Hamiltonian and general case is commuting local Hamiltonian is always frustration free. So that's why I mentioned QMA1. But that's all we know. In a summary, like commuting local Hamiltonian is simple but quantum. So yeah, so to be more precise, we say the commuting Hamiltonian is something between classical and quantum. And the key, so in this talk, we'll care about two different questions. One is, okay, it's less in between classical quantum, but what's the precise answer? Like, is it really NP or is that hard as general case? or something in between. And besides that, we also care about like the ground state of commuting the Hamiltonian. Like, is it easy or hard to prepare? Whether it's highly entangled or less entangled. And in particular, I will use the terminology like trivial ground state to describe a state which can be prepared by constant depth circuit. So anyway, in summary, we have introduced what is commuting the Hamiltonian, and I want to spend some time explaining like why you should be interested in this problem. So, like as I said many times, commuting the Hamiltonian is simple but quantum. So, from complexity view, like since you have more structure for commuting Hamiltonian, so it may be easier to use commuting the Hamiltonian to tackle many hard problems. So, for example, you can study a commuting version of quantum PCP, and also like the NLTS conjecture is proved by constructing a commuting Hamiltonian. And besides, I think recently people get more and more interested in Gibbs preparation. Like yesterday's talk all focused on Gibbs preparation. So commuting the Hamiltonian is also a very good test ground for proving mixing time. It's like it's a test ground for you to generalize classical techniques to the quantum world. And besides, if you are interested in ground state preparation, you can also first study a commuting version. So that's a complexity reason. Okay, any question?
So I just had a question about the previous slide, but I can ask later.
Okay.
Yeah.
Okay, that's fine. And from physics view, people are also interested in this Hamiltonian because commuting Hamiltonian captures some very quantum phenomena like topology order and like evergreen codes of quantum memory. So okay, we have introduced commuting the Hamiltonian, and we have explained the motivations. So next question is like, okay, fine, it's interesting. So what's the known results? So in one sentence, the current result can be summarized as we know some special case is inside empty. So there are quite a lot of people have ever thought about this problem, and there are many results. I don't want to list them. Okay, so basically, all of those results can be classified as two cases. So as I said before, commuting the Hamiltonian is simple but quantum. So basically, those systems can be classified as a classical system, which has trivial ground state, or some quantum system which has no trivial ground state. So based on this classification, for two local and three local case, those systems are always some subclass of three local case. Those systems are always behaves like a classical system, where the ground state is of neutral entanglement. But when you come to four local, like on 2D lattice, it will contain story code, so we know counterexample. And we know those systems might be very highly entangled. And besides those two kinds of results, there is another 9, which study the factorized case. I will only briefly mention this case. And one more remark is like some of the results are constructive. So what do I mean for constructive? So for constructive, people really characterize the ground space. Like they provide the instructions to how to construct the ground state. So due to time limit, I will only talk about the simple version of them. But I would like to advise the next talk, where Isaac will talking about his new results, which is related to ground state of commuting Hamiltonians. Okay, so factorized just mean like every term is a tensor product of single QD terms. Yeah, I will explain this later.
And
could you remind us like what trivial meant here? Like what circuit depth is non-trivial, like log or?
Yeah, log. Like and cannot be prepared by constant depth circuit.
Oh, okay. So the toric code counts as non-trivial.
Yes. Yeah.
I think you have like all-to-all coupling for the circuit.
What's happening?
Gates can act on any pair of qubits, or is it supposed to be?
Factorized case.
Oh no, no. When you say non-trivial, like
Oh.
you mean like gates can act on further qubits, or is it a geometric locality?
Yes, I think it can act on arbitrary qubits. Yeah. So I mean, the trivial, why constant depth is trivial? Because you can use light cone argument to verify the energy. So that's why it's close to classical.
And is there an interesting class of circuits that can be encoded into commuting Hamiltonians that's beyond classical circuits?
Stabilizer?
Or do you think stabilizer can be encoded into?
I mean, all stabilizer Hamiltonian. So there are different things. So one is the Hamiltonian is commuting.
Right.
Another one is the circuit is commuting. So the unitary for commuting no Hamiltonian, I mean, to diagonalize it might not be commuting. So that's why this problem is hard. So any other questions? Oh, sorry.
Maybe that one, but why does the 4 local 2D qubits result not imply the 4 local 2D Q-tricks result?
Yeah, that's a very good question. We will. So the intuitive reason is because it's something like the difference between SAT and CSP. So when you increase dimension, you will add degeneracy, which will mix up everything. Like 1 and 2 have difference.
Okay, so it's not necessarily implied.
Yeah, they're very different. And the QD case is a big open problem. Yeah, but I will explain this in more details later. That's a very good question. So that's a current state of art. In this talk, we will mainly focus on to keep focus, I will mainly focus on the complexity view. It's like we will assume we want to prove commuting Hamiltonian is inside MP. And I will talk about some toolbox and technical challenges. So to avoid you get lost, I want to first talk about what I'm going to talk. So in the rest of the talk, I will try to intuitively cover 3 different ideas, where each of them is try to circumvent some obstacles of previous one. And if you think that's too much, I strongly suggest you to stay for 5 more minutes. because I'm going to talk about that's enough to understand structure lemma. So I'm going to, which is the most important technique for commuting Hamiltonian, in my personal opinion. After that, I will talking about interesting technique which connects commuting Hamiltonian problem to some problem of computing trace. And after that, I will talk about the self-reduction method. Okay, so let's begin with the most important 5 minutes. So this technique is called structure lemma. So if you ask me to summarize this problem in 1 sentence, structure lemma says 2 local commuting interaction will always imply decoupling. So what do I mean? So imagine we are working on 3 qubits or QDs, and we can say the 2 terms H1 and H2, and they overlap on the Q. And the question you may ask, okay, what's the ground state of H1 plus H2? So since they have overlaps, so the ground state in general can be an entangled state on 3 QDs. But imagine if we are lucky, like if every QD is a tensor product of 2 QDs, in the sense that H1 and H2 has no overlap. So H1 and H2 will correspond to the edge. So in the extreme case, in the bottom picture, H1 and H2 has no overlap. Then the ground state is easy. It's a tensor of 2 QD states. So you may ask, that's cool, but what's the relationship with commuting? So the most important thing is like commuting, in fact, implies such decoupling. So what do I mean? So more precisely, if H1 and H2 are commuting, then you can decompose the Hilbert space of Q as direct sum of some small space, which is invariant under 2 terms. So this may sound a bit mysterious. In other words, I'm saying like under this decomposition, H1 and H2 are block diagonalized. So we know there is one ground state which lies in one of the subspace. So to get the ground state, what you need to do is like choosing a subspace, and then find the ground state in this subspace. And more important is like in every subspace, you can do such decoupling, in the sense that H1 and H2 has no overlap. So that's the most. So this is the most important technique for commuting Hamiltonian. So this is called structure lemma. So basically, I'm saying like this would imply the ground state of H1 plus H2, in fact, can be prepared by constant depth circuit. So the first layer would be choosing the local basis, which to get this decomposition. And the second layer would be to prepare the tensor of two Qt states. Any problem?
Yeah, so if the commuting can directly imply the coupling, then why you need to local?
Yeah, that's so that's a very good question. It's like you can only so I mean I write two local. It's because to use this structure lemma, you need star-like interaction. You need all terms intact on a single qubit. But I think I have a better picture in the following slides, so I will explain this. Okay, this is what I mean. Like, so like if you consider general two local interactions, the key property that why we need two local is for two local case, all the terms will always overlap on the same qubit. I mean, if they overlap. I will explain why this doesn't work for 2D, for local case later. But temporarily, you might just remember like the key fact of structure lemma is you need all the same has a star-like interactions. You can keep this problem in your head because when we come to for local, I will talk about why this doesn't work. So.
And you can keep doing this on other qubits as long as it's a star-like.
Yes.
Is it to find the ground state?
For this ground state? Yeah. Yes. Similarly, as I said before, it's like, so by doing, also the decoupling method is just like, by choosing subspace, you will like sequentially doing this, and then finally you will get a Hamiltonian where all terms has no overlap. So the ground state, again, is some kind of trivial ground state. So I mean, in summary, for any two local commuting local Hamiltonian, its ground state is always trivial. And this would imply this problem is inside MP because you can use the constant depth circuit as witness. And to certify the energy, you use a light cone argument. So you can certify the energy classically. So that's why this is inside MP.
Yeah. So the dimension of these 4 nodes that you added has to sum up to the dimension of the left one. What's the relation between them, actually?
Yes, like, I mean, so first, if you back to this picture.
Yeah.
So the dimension would be sum of those dimensions.
Okay.
So it's decoupled after you choose the subspace.
So can I confirm I understand that picture? So that picture, the 4 dots in the middle
Yes.
are a tensor product of 4 spaces. Is that right?
After choosing subspace.
So
Yes.
Basically, that single green dot has been expanded into a direct sum of spaces. Each of those spaces look like these 4 dots.
Yeah, exactly. Yeah.
And you need NP witness because you don't know which subspace might be empty, so you have to.
Oh, yes.
Otherwise, it is all.
Oh, yeah. That's a good comment. Yes. So for NP witness, you need an index of the subspace you choose, and another one is the constant depth circuit. Okay, so we have finished the most important part.
Sorry, can I just ask something? So does that mean if you're in the case with trivial center, so you don't have a direct sum, does that mean put it in unit always in P?
Sorry, say again.
In the case where there's a case where the algebra has a trivial center, so then you don't have an index. It's like you don't have a direct sum, you just split it into a tensor product, and there's only one sum.
Oh, yes.
That's then always P, is it? I guess.
Yeah.
Okay.
Yes, yeah. Yeah. So as yeah, as some audience already asked, it's like, why can't we do this for everything? Like, yeah, we say structure lemma is very cool. Like, why can't we just use this method to prove general cases inside MMP? So like, we know you can't. It's not only because we don't try hard. It's because we have counterexamples. So as you may already see, like from this picture, like structure lemma always imply some kind of trivial ground states. But we know there are counterexamples. We know like toric code, which is a commuting Hamiltonian, which does not have trivial ground state. So in principle, we know that this method doesn't work for general case. Okay. And yeah, and to try to prove this. Sorry.
Is it NP hard?
This problem? Yeah. It contains for two local cases. It contains CSP. It's a max. It's not really 2 set. It's max 2 set. So it's NPR. And in this case, it also yes. So okay. In summary, what we did before is like we know structure lemma is powerful. It's able to prove two local case. And we know structure lemma has limitations. It cannot work for everything. Like, and we know the hard case lies in 2D lattice. So to prove 2D case is inside MP, we need new ideas. Okay, I will explain why structure lemma doesn't work for 2D to answer your questions. And then I will talk about intuitively talk about two techniques to do better. So, okay. Before we go into details, let's first briefly define, like more formally define what we are going to do. So, what is QD commuting Hamiltonian on 2D lattice? It's like we consider a 2D grid, and on each vertex there is a QD, and on each plaquette there is the Hermitian terms. So there are some other settings which put QDs on edges. Those settings are equivalent to my current setting if the underlying graph is 2D lattice. Because 2D lattice is dual to itself. So for simplicity in this talk, we will assume all the PR projections. And the problem would be, okay, given H, which is the summation of projections, we want to ask whether the ground energy is 0. Or in other words, we want to ask whether all the P's have a common 0 ground space. So that will be our focus in this talk. A remark is that we can handle general case, but it's just simple for this talk.
So if they're not projections, then you cannot make them projections, right? Because you lose commutation structure. Like if they're not projections, then.
But you can use the NP prover to choose the eigenspace.
Oh, okay.
Yeah. So commuting is always, if you allow NP prover, it's always frustration free and can be reduced to this case.
By keeping commutation, by keeping them commuting.
Yes, because two terms are commuting, then any eigenspace are commuting.
And these terms are now for local. They just act on the vertices of each square.
Yes, it's for local. Yeah. So this will be our main problem for the rest of the talk. And our goal is try to prove this inside MP. And in other words, we try to provide a scheme to say, okay, even the ground state might have high entanglement, might not be trivial, you can still certify the energy by classical methods. So that's a key focus. So let's finally come to an intuitive explanation, like why structure lemma doesn't work for local case. So as I mentioned before, like the key concepts, like the key property of two local interaction is like it always interact as a star. So you can decouple all the terms at the same time. So what's wrong when you try to do this for local case? So for local case, of course you can use structure lemma, but you will get incompatible decomposition. So what do I mean? It's like, of course you can, if you only consider P1 and P2, there will overlap on like the orange QDs. You can use structure lemma to get a decoupling method. And if you consider P1 and P3, the overlap on the blue part, you can get another decouple, some kind of decomposition of space. But those two decompositions are incompatible on Q2 because, I mean, they overlap on different qubits. So that's why structure lemma can't work. And also, we know there is counter example, so we know this doesn't work. Okay, everyone is good for this. That's good. So yeah, so now we are in the most technical part in this talk. So we said strict lemma cannot work. So what's the new idea? So about 10 years ago, like Norbert gives a very beautiful and mysterious proof to show that. Sorry.
You mean qubit or qubits here?
Here's qubit. Qubit is an open problem. So we only, you can only prove for qubit. Yeah, okay, everyone knows. I need to explain what's mysterious. So, I mean, all the proofs we have seen before is like proving something inside NP by, I mean, explain what's the ground state, right? For example, like in two local case, what's the NP witness is like we give the description of the ground states and then say, okay, you can certify the energy. So why I say this method is mysterious is because it proves the ground energy without knowing the ground state. So, okay, that's a good why. So let's recap what we are doing. Like, we are given some projections, and we want to certify the energy classically. So I think the key summary of Norbert's proof is like he realized you can transform commuting to Hamiltonian problem to some problem of computing trace. So what do I mean? So if you write pi p as a projection onto the zero eigenspace of p, then like you ask whether the ground energy is zero is equivalent to ask whether all the p's has a common zero eigenspace. So I mean, you can feel free to imagine all the pi p are diagonal, and you're asking whether it has a common zero eigenspace. It's equivalent to ask whether the product of them has non-zero trace. So the product of them just the eigenspace of is just a common zero eigenspace of everything. So this is what he observed. Since we are working on 2D lattice, like we can write this product in a more beautiful way. So if you write PG as a product of all the gray term, so when I say gray, I just mean like as a picture, you view the 2D lattice as a chessboard, and you just group all of them, the gray term and the white term, and then the observation is like proving the ground energy is zero is equivalent to proving the trace of PG and PW is greater than 1 or greater than 0. If you get a little bit confused here, that's fine. I mean, all you need to remember is we are going to prove this is greater than 0 in the following problem.
Will this only work for the square lattice then?
This works for anything, but for proving this, you need the property of 2D lattice.
Okay.
Yeah, so this fact works for anything because this is just linear algebra.
So if it was a hexagonal lattice and you had 3 layers, then you
Yeah, that will be problem.
it won't work, right?
Yeah,
It will be ABC.
Yeah, we will see why. So, sorry, any problem? Okay. So like what we are going to do is to just prove the trace is greater than 0. So you may ask, okay, why this is easier? It sounds just like a very simple linear algebra argument. So let's again first look at the extreme case. So suppose all the gray terms are, product of pure state, and all the white terms are also product pure states. Then computing the trace is easy because you can trace each QD individually, and you just get something like this. But of course you can ask, okay, how about the hard case? Like because we know toric code is a very good counterexample for everything. So I say you may ask, okay, how could we do with toric code? So the key fact is, computing the trace of toric code is still hard because of high non-rigid entanglement. But however, you can somehow map the Tory code problem to the simple case. So what do I mean? I mean, so we know all the x term, for example, this term, they diagonalize in the plus minor spaces. So you can decompose every term in plus minor spaces and decompose all the z terms in zero basis. Why this makes problem much easier? So in summary, I'm saying like we can decompose the trace in the left-hand side to be exponentially many terms, where each subterm is very easy to compute. So the key fact why this makes everything easy is because the key fact is like you notice like so in summary what we do is like we write a sum, write the term into a summation of non-negative terms. So it's because so first because all the values and values should be non-negative because we assume pi j pi p are projections, and all the subtrace will be non-negative because it's a product of two projections. It's trace PG, PW. This is where we use 2D lattice. The most important thing to notice is that if you want to prove a summation of non-negative term is greater than 0, the only thing you need to do is prove one of them is greater than 0. So that's a key idea in this proof. And the NP witness is just the index of the non-negative term. And each term can be easily verified.
Is there a more operational view here? As in, could you see something like you're measuring the other layer in the basis of the first layer, something like that?
I'm not sure. Like, yeah. Yeah, so like I think this proof is very elegant because it says nothing about the ground state. Okay.
Why you need two? Why two is special? Like you have PG and PW. What if you have 3 and 4?
Yeah, because so the trace of two positive observable positive matrix is greater than 0, but the trace of 3 of them are not. That's the reason.
Don't they commute in this case?
Sorry.
They commute.
They don't. Okay, so PG and PW, you mean? After projection, they don't commute. Yeah. So this part is some kind of brute force computation. So okay, I think we already get the intuitive reason about Norbert's proof. And for general case, what you do is like classify some qubits, and some of them will behave like a Tory code or in some sense. And if it's not the case, there will be a lot of identities. And so what I mean is like what you need to do is like decompose the trace whenever whenever it can apply, and then the subtrace will contain the qubits on B, which has quite a lot of identities. So you can imagine like the subtrace will have very limited interactions. In particular, it will have 1D structure, which can be again verified by P. And the subtrace will be the NP witness. Oh, sorry.
Go back 2 slides and another one, please.
This.
Sorry, maybe
Okay, we can talk offline.
So basically, is that lambda h is equal to 0 is equivalent to a trace of the product is bigger than 0.
Yes.
Could you explain again?
Because the ground energy 0 means all the P has a non-zero eigenspace, has a common 0 eigenspace. So because the product, we are taking product of pi P, so this is I minus P. Probably I can. Where do I answer your question? Okay. Okay, I can explain to you offline. Anyway, so I just mean like intuitively we can prove QB case is inside MP. This is highly long constructive proof. People are still also curious about the ground space. Like, in fact, some about 7 years later, another group make a constructive proof. It proves the qubit commuting Hamiltonian is in fact equivalent to torical permitting boundary. So I won't explain this in more details, but what you need to know is like from this proof, it claims you can prepare the ground states similarly as how you prepare the toric code. It's like by polynomial circuit, wire a Mayer and correct operations. One more sentence is like the equivalence to toric code means like for some qubits, all the terms will looks like a toric code. So okay, that's all we have for qubit case. So yeah, like Sunny asked, I mean, why this only works for qubit? It's because when you increase the dimension, things will become more complicated. Like even you increase one dimension, it will bring degeneracy. Technical reason is like the subtrace is no longer a 1D structure. So I mean, to prove for QD case or Q-trade case, you need like new techniques. So I had a recent work with Sandy, like we get some new results for the QD case. So the first result we get is we will prove the Q-trade case is inside MP. So compared to Norbert's proof, I think our proof is even more mysterious. Okay, why is it so? Like I'm saying like, I mean, imagine a set. For set problem, you can do self-reduction by choosing the bits, by fixing a bit. We also do a reduction, self-reduction for commuting Hamiltonian to decrease the dimension. So like how can we do something like from Q-trade to qubit? We do self-reduction, but we did some kind of rounding. So we round the Hamiltonian to another commuting Hamiltonian. So that's why I think it's mysterious. I will briefly explain this. So for QD case, we also get the factorized cases inside MP. So where factorized just means like every P is a product of single QD terms. And for this, we get a constructive proof. We prove is somehow equivalent to stabilized Hamiltonian. A remark here is like, so in fact, you might think this sounds reasonable, but in fact, factorized Hamiltonian can look very different from stabilized Hamiltonian. So what I mean is like for stabilizer, everything will always commute in a very regular way because everything is poly. So they either commute or anti-commute. But for factorized case, they can commute in a very weird way. So for example, if you consider two terms, if the first part orthogonal to each other, then the two terms commute no matter what is AB. So that's why it looks strange. But again, we claim we can prove this is somehow equivalent to stabilized Hamiltonian in the sense that we prove the ground space looks like a stabilized Hamiltonian. Okay, I have several minutes. That's enough for the mysterious part. So in the following, I say like from previous work, we know how to prove qubit case, and we said we design a very mysterious method for Q-trade case. What's that? So recall our goal is to, prove the energy zero, and we want to decrease the dimension of QD because we want to make a reduction, make it back to the qubit case. So how could we do that? So let's begin with a trivial example, like where there is a separable qubit. So for separable, just mean like, so we're looking at the qubit Q. So we suppose there is a decomposition of Q such that every term is block diagonalized in this term. So in this case, we know the ground space must lies in one of the subspace. So at the NP prover, you can just choose the subspace and say, okay, I will prove ground energy for this subspace. By doing this, you do a self-reduction because you decrease the dimension of the particle. So this is a trivial case. The key fact we notice is like, for commuting Hamiltonian, we can do something more fancy. It's like so imagine you have a semi-separable qubit. What I mean is like we again consider decomposition, and we consider four terms acting like this qubit. In this case, we allow the first three terms will have a block diagonalized decomposition. But we allow the fourth term to be messy. So what we realize is like, even in this case, we can again do a safer reduction, a non-constructive version. So what we do is like, as empty prover, you will choose the subspace. And for the first 3 terms, you can naturally restrict everything in the subspace. But for the fourth term, because everything is messy, like what you need to do is just brute forcefully project this term in the subspace and rounding all the long 1 eigenvalue to 0. So that's how you get a new Hamiltonian. What's more important is like we prove like we are not doing something like random. We are really doing something reasonable. It's like we prove like the original Hamiltonian has 0 ground energy if and only if there exists a subspace where the ground energy is 0. So this is similar to the separable case, like the ground energy is 0 as long as one of the subspace has 0 ground energy. Yeah, I think that's a. So and one thing I mentioned is like this lemma works for any QD and any geometry. It's not only for Q trees and the 2D lattice. Okay, so then is the final pages. It's like open problems. So I think the most interesting open problems is like what's the complexity of QD case. So I personally believe it should be harder than MP, and I conjecture it might be a long trivial class in QCMA. So that's why I think it's interesting. And also I think if you care about the ground space, I think prepare the ground states of 2D commuting Hamiltonian might give intuition for some very important problem like Avery law or something like this. I don't have time. Okay, I think I should stop here. Thanks.
If there are any quick questions, otherwise we should take questions offline. Any 1 second questions? Great. So we'll have now Isaac